This is part 1 to an ELEKIT TU8100 Class A vacuum tube amp. That's that little 2-watt 2-tube amp. I had one of my viewers sent me one that he built, and it doesn't work into troubleshoot. I got to get parts for this one, but this is the troubleshooting and tear down of this little unit and figuring out what part went wrong. Let's check it out. So I had a viewer sent me in his ELEKIT 8100. This is the little PCL86 amplifier that I've built one of these kits, and his is shutting down after 30 seconds. He said it goes into shutdown mode. I've got my own here as well for comparison. Mine has put the sticker on mine. I guess this sticker was probably supposed to go on the front here, but oh well, my sticker went on the top. And we can compare the two. Now, he didn't send his power supply in, so this is my power supply. I'm going to hook his amp up to my speakers, and we'll see what happens with his amp, and then we can do some comparison. He didn't send me the power supply, which is unfortunate because I can't do live comparison between the two of them. If we're going to do any voltage measurements, I can't do them both at the same time for comparison. I'll have to do them one at a time. But let me get the speakers hooked up here first, and we'll see if his is doing the same problem as mine. Before I get started, I'm just going to put because I might be swapping tubes around just to see if he's got a bad tube that's causing it. I'm just going to put my initial on my own tubes, just so that I know that these ones are mine. There. So now I can ID that these tubes are mine, so that they don't get mixed up. Okay, let's turn it on and see whether anything happens. Okay, the tubes are starting to warm up. Let's see if we get any sound. I've got my MP3 player plugged in, delivering sound. Okay, we're getting sound, and he says it shuts off after 30 seconds. So let's just see what happens. That's the end of the song. Okay, it looks like it just shut down. The LEDs below the tubes are blinking, and these it has gone into a shutdown mode. You can see his LEDs are blinking. So they're going into a shutdown mode after it runs for about 30 odd seconds. It should be noted that if you try to run them without the tubes, they will go into shutdown because it does monitor the current that the tubes draw, even in standby. So you can't turn this on without tubes in it and expect it to stay on. It will shut off. Mine does the same thing. If I power it up without tubes, after 30 seconds it'll do the blinking LEDs as it shuts the power supply down to protect everything. And there it goes off. So the power supply is shutting down. One thing we're going to check first is we're just going to check with my own tubes just to verify that it's not an overload condition caused by a bad tube. So I'm just going to pull the tubes out of my unit, and we'll put the tubes into this one. And verify that we get the same fault. Now my tubes are very old. They have tons and tons of hours on these ones. Okay, so got the same fault. The high voltage is shutting down to the tube, so we know it's not a tube related problem. So now I can take this thing apart and we can start to troubleshoot. I got to dig up the manual for this thing because I don't remember what I did with the manual for mine. It's been so long. I built mine, how long ago? Probably 3 years ago at least. It was the first of these kits, these ELE kits that I put together. And I also built the bigger one, the 8200, which I use on a regular basis. So it's been a while. This one here, the manual was all in Japanese too, which was kind of a pain in the ass. We'll take this thing apart and start doing some testing and see why this thing is going into a shutdown mode. Top off. Generally, when I see kits that aren't working, it's because somebody messed up when they were building it. So the first thing I have to do is I'm going to inspect for things like capacitors installed backwards. These ones all look good here. This is the amplifier board, but the ones that are likely to cause a problem are going to be the ones in the power supply. So things like ferrite bead 2 and 3, 1 over here, this capacitor here, these two over here, C11 and C12, could certainly, if one was installed backwards, it's going to draw too much current, which is going to shut this thing down. It's going to put it into protection. Also, this whole setup here, the whole power control is monitored. So it's monitored for overcurrent, over voltage, under voltage. So any part that's installed incorrectly or put in backwards, for example, could cause a problem with this. So the first thing I'm going to do is I'm going to remove the actual amplifier from its case so that I can get access to the power supply board, which is this one on the bottom here. That way I can inspect all the connections, inspect for any parts that may have been installed incorrectly. That's not very tight, that screw. Remove those two screws, and remove the screws in the back here. And there's the base off of it now. So now I can inspect the solder connections on here. Get my light over so that I can see what I'm looking at. Now, I should be able to remove this board if I remove these nuts here. Or even the screws on the top here. I should be able to swing this board out of the way so I can see what comes out with it. This one's soldered in, so yeah, I gotta remove these screws. It's been a while since I put mine together. As you can see, I'm having to kind of figure out what I gotta take apart on this thing, because these units here are, a lot of these boards are soldered together with each other, but they do come apart. Okay, I should be able to lift this. Oh, I gotta take out this screw on the jack panel at the back. And now this should lift up if I'm not mistaken. This should lift out and lift up. Take this little circuit board off the back here. Okay, now I can lift the board out and remove some of the shielding here so that I can observe Now what I'm doing is I'm paying close attention to this area here in the FETs in the primary side, because all it would take is a connection problem, one bad connection in here, and it's going to upset the balance, which is detected by the drive IC, which will shut it down if it detects that there is a fault. So I'm going to do a very close inspection of the soldering here, and let me see if I can check these connections out and see if there's any of them that look like they might be suspect. I'm going to redo them. I'm going to redo some of these connections so that I know that they're done and heated up properly. So I'm just going to resolder this board and then we'll give it a try. Have these pass-through connectors. We'll check our ferrite beads, FB1 and FB2. Okay, I should have 12 volts always on ferrite bead 1, which is this one here, which I have 12 volts. And when the power switch is turned on, I will get 12 volts coming back to, I should go to IC2, which is the 5 volt regulator, which will then charge up C19 and turn on power to pin number 14, 5 volts, to the PIC, to IC1, pin number 14. Will be the one that gets power once it's turned on. I'm just going to turn it over. So now, if I turn on the power, I should see power coming up on the, well, the 3-terminal regulator over here for starters. Where is it? There's my 12 volts. There's my 5 volts, so we get power to this unit. Tube should be heating up. Let's see if we get any sound. Yep, the lights are on. Let's see if we get any sound and see if it stays on. Okay, it just shut down. So now we can do some more investigating. So pin 3 on the pick over here is the B plus check, for the check to make sure that the B plus is working. So let's just monitor this. It's 0.04 volts right now. There it goes, now the voltage is up, it's a half a volt. It's climbing. And then it just went off. So that is, the power went off. That's pin 3. This is our abnormal power. And it picks up its source from the, it senses off of the 200 volt supply through R470 and then through R40. So it's a 470K followed by, and then shunted to ground with a 2.2K resistor. So that is getting, it is getting its feedback, so it knows the voltage is on. I'm just going to look at the cathode to the pentode pin 7 and check the cathode return voltage, because this is also monitored. So let's just fire this thing up. We'll watch the voltage here. These units will shut down if there's no tubes in them. Like if you pull the tubes, it will go into a shutdown because it monitors the cathode current for both tubes. So if the cathode current is too high or too low, it's going to go into a shutdown. So here we go. We got being a Class A amplifier, we're going to have some voltage here. 2 volts on this one. So we're at 3 volts here. Even when there's no sound, we'll still have about 3 volts. And then it goes off. So one of the things we can do here is, I have a donor amp. So I've gone and I've taken measurements of the IC pins. And what I can do is I can compare the voltages on this amp with one that I know works. So we got to turn this on. We're going to have to do this obviously while it's working, because once it shuts down the voltages won't be correct. But we'll turn it on and we'll just watch the voltages. Starting at pin number 1 should be 0.38 volts. We'll see if the voltages go to different voltages once this thing turns on. So that's climbing. It's climbing much higher than 0.38. This is probably why it's shutting down, because this voltage is getting beyond a preset. There we go, and now it's shut off. So pin number 1. Let's look at what pin number 1 is. Pin number 1 and pin number 2 sense the voltage coming back from the vacuum tubes. They sense the cathode current. So if the tube is drawing too much current, it means that it is biased too high, and it is causing excessive plate current, which of course will lower the voltage. My plate voltage was only coming up at 210, and it should be around 220. So that would explain something here. We may have a biasing problem on the tubes. So that was pin number 1. Let's look at pin number 2. It looks like the biasing problem might affect both of them too, because normally what this will do is if one's over biased, it'll just flash the one LED, but the fact that this is doing both of them is an indication that it's a common problem for both. So we'll watch pin number 2, because pin number 2, although on mine it was 0.11 and 0.38, they will be slightly different because the tubes themselves are going to have slightly different characteristics, but this one's climbing way up too. It's at 0.6, 0.7 now coming up. See, we're sitting at 0.6 now. It just shut down. So I think this is where our problem is. I think our problem is it's going into protection because the tubes are getting into runaway. And this is measuring the cathode current. And the cathode current is set by how much current is able to flow through the tube itself. We've got to remember that these are Class A amplifiers, so there's always going to be cathode current. Even when there's no sound, there's always going to be a certain amount of plate to cathode current. That's the way a Class A amplifier operates. The control grid, which is off of pin 8 here, controls how much plate current will actually leak through. It's signal that drives it comes off of pin 9, which is the plate from the triode. If I zoom this camera in so you guys can see what we're talking about here, because of course my printer's got a nice big line, but let me try and draw this in. Get my pen and we'll try and draw this in as to how this thing works. So our audio goes in pin number 1 of the tube. We'll look at this tube for example. Here's our audio. Our audio comes in here, right, into pin number 2, or pin number 1, sorry, which is the grid of the triode. It's amplified and our bigger signal comes out here on pin number 9. Pin number 9 continues along. It's coupled through this capacitor. This is a blocking capacitor. It's designed to block the DC voltage, because if it didn't block the DC voltage, we'd be applying full B+ to our grid and the tube would avalanche and go into full conduction, and then you'd have big time problems. So this capacitor is a blocking capacitor. If this capacitor were to fail, we'd have too much plate current and we'd go into shutdown. Otherwise, if it didn't go into shutdown, the tube would go supernova and that would be the end of the tube. So we monitor the current going through the cathode here. The current here, the cathode, gets monitored. R18 is our cathode resistor, and it gets monitored and it's fed back all the way back down here to the monitoring inputs. This PIC controls everything. It could be the PIC is defective. That's one thing it could be, is this PIC itself could be defective. Now these won't operate without tubes, because if you remove the tubes, there'll be no loading, and the high voltage generated here on C13, see, this is also monitored right here through R39, which is a 470K resistor. This is an over voltage monitor that monitors, and it shows up at pin 3. And I haven't measured it at pin 3. I should compare it to my amplifier as well, but I think we'll find that this one's probably low, because I think the high voltage is a little low. But both tubes themselves are going to be biased from a common source. This one's referenced to ground through these two resistors, R15 and R16. And our reference is taken off of the transformer here. We have our B+ coming into the transformer, which goes to the plate. So here's our reference, right? Our reference here goes into the transformer, goes through the primary, and then over to the plate. And our reference also goes right into pin number 3. So this is our B+ voltage here going into pin 3 of the tube. And that's what biases the tube. That and what is arriving at pin number 8. If the voltage at pin number 8 is too high, the tube will go into conduction. So that's reference to ground over here. So we could have a grounding problem over here on this ground. That could certainly cause a problem. That ground goes back, it ends up back at the heater FET, but it's also grounded here on the board. So if that ground were to be were not to be good, that could cause this voltage to rise. If the voltage rises here, it's going to cause excess conduction through the tube. So let's just investigate this ground off of R16 and R15. So R16 and R15 are, where are they? R16 and R15. And they go through to this ground here. That's it there. Let's just measure it. Get the meter, where my probes went. So R16 is this, R15 is there. As you can see, 0.7 ohms, which is, or 0.5, that's good. And where is it grounding? It grounds back to this other board. And it should be the same. It should be grounded. That should be grounded to pin number 5 of the IC over here. Let's just see where they got a good ground. 1, 2, 3, 4. Oh, is that 5? I think that's 5. 1, 2, 3, 4. Pin 5. Oh yeah, there we go. We got a ground. Okay, that's good. So our ground is good. Therefore, our bias for the tube should be good. But our voltage is rising here, so we're going into conduction. Let's just look at pin number 3 for the vacuum tube and watch the voltage here. We got 12 volts on it when it first starts. That's fine, because 12 volts is actually fed in through the transformer, and then the boost comes on and it should boost it up to about 220 volts. There we go, 230, 240, that's good. And then as the tube goes into conduction, it drops. Down to about 205 volts now. As you can see, it's settling in around 204. Now it shuts off. And we go into that shutdown. I'm just wondering whether that's dropping too much. Let's check some of the other voltages on the drive IC here as it operates. Let's see what the rest of them look like. So pin number 3, mine goes up to 1.02 volts on mine. We'll see what it goes to on this one. I think it's going to be low. Okay, 1.0, now it's starting to drop a bit, you see. Now that the tubes are going into conduction, it's dropping a little bit, but that is to be expected, especially if the tubes are drawing too much current. And it's playing now. Pin 4 should be 5 volts, which it is. Back to pin 3. And then it cuts off. Pin 6 should be 5 volts. I think pin 6 is probably... pin 6 is the heater control. So that's just an output that's switched to turn on the heater. Pin 7 is a control voltage. Let's see what pin 7 looks like. 0.7 volts, that's right. And that's switched by the power switch, so that should stay on regardless if it's in shutdown or not. This should stay on. And it will. Until I turn the switch off. There it goes off. Pin 8 and 9 are not in use. That's why they measured 0. Pin 10 is current loop, I believe. So it should be like 0.117. So we'll just watch this. This is current for the FET. So this is the feedback circuit here. Pin number 10. 10 and 11 are the feedback from the drain. For the FET. So 0.117. See, it's going too high. The current is going too high. And here, oh, this one's got nothing on it. Interesting. This should both be the same. This one's got nothing. So maybe this is our problem here. This is pin 11. Yeah, okay, let's take a look, because pin 11 should be about the same, about 0.11, and it's 0. So pin 11 feeds back through R37, and that goes up to the source. No, the drain. Sorry, the drain. It's hard to read this because of the line through it. The drain for FET1. Is the drain or is it the source? Source. Source, yeah. Drain goes to the drain. Is this one? Source. Source here on FET1. There's nothing on that one. That one's got 0.2 volts. Volts, 11 volts, 2 volts on our gate, nothing on this gate. So we're not being driven on. So that's pin 16. I gotta look over here. Maybe this IC is not driving it. I saw a waveform when I looked at the drain, but that again, it would be picking up the signal from the other one, the square wave. So how these operate is that the two FETs switch back and forth. One switches on when that one's off, and then vice versa. They just go back and forth like this. It's driven from the IC. So the drive for that is off of pin number 16. So we should have 2.35 volts on pin 15 and 16. So it's pin 15. I said it was 15? 15 drives FET2. Pin 16. Let's see if we have a drive voltage here. It might be the IC's popped. If we're not getting a drive voltage from here. If we're getting a drive voltage from here, it's not arriving at the FET at the gate. Ah, nothing. That one's got voltage, you see? And that one's got nothing. 0.2. Let's just see if there's a waveform on there. So look at 15 first. Oops, shut off on me. Okay, I gotta wait for it to reset here. So we're gonna look at pin 15 and pin 16. So this is pin 15. Turn it back on here. You'll see the waveform come on as soon as the as soon as the pick starts sending a drive signal. There we go. Okay, there's our drive signal to drive the FET, and here's the other one. Much lower, and that FET is not being driven on. Either that or the FET's foobar. We can pull the FET out. Oh, this is going to be fun. Wonderful. We can pull this FET. There's another FET in here that's used for the filament control, which I could short that. It's not really necessary that the filaments come on. It just turns them on and off. I could short that and leave the filaments live without having them turned on. It just puts a delay on them if we needed to. But I'm just going to try and take this FET out and see whether we get a bad FET here. It almost looks like this FET is kind of foobar. So what I'm going to do is I'm going to remove the FET and I'm going to turn it on without the FET installed and see if my drive signal comes back. If I get my drive signal back without the FET installed, then it's pointing towards the FET. If the drive signal is still not there, then it could be the driver inside the IC is popped. Hope not that, because that's a pick that would have to be ordered from the manufacturer of the kit in Japan. And then it's going to get a little more expensive because it's already cost the guy that owns us a small fortune to ship it to me, but he couldn't think of anybody else to send it to. And since I have experience building these things, I've repaired a number of these amps for people. I haven't done videos on them because I've had a few people that have hired me to build them amps, right? Like the 8200 that I've built 3 of them, and I've had people pay me good money. I've been paid like $400 to put one of these together. Not one of these, but the 8200. I got paid $400 by a couple people. I think I'm charging too little. I should be charging more than that for the amount of time that it takes to do it. But I've done like 4 of them, including my own, 3 for other people. But yeah, it's I get people that they want one built and they want it. They're scared of tubes, but they want the tube sound, and they're scared of working with vacuum tubes. So one of the suppliers or one of the shops that sells them has given people my name, and I've been contacted by 3 people that bought them and put them together for them for a fee. But I didn't shoot videos of me putting them together because, well, I've already got a video of me building the first one that I built and building one of these, so there's no point in doing another video of the same thing. But I've put a few of them together, so you get to know these ones once you work on them enough. Once you work on them a few times, you get to kind of know how they work. Gonna have to try and heat this up. It's soldered down to the board as a heat sink, so I got to kind of melt the solder here and kind of lift it up. So that I can pull it through. Okay, now I can lift it when I heat the pins up. I should be able to lift it out. I think I got all the solder out there. Maybe not. Yep, I got it all. Okay. Now it's just a matter of heating the pins and removing it. So there's the FET that I suspect might be foobar. Enough solder on there, man. Let's just check the waveform and see if the drive comes back on the gate. If we get the drive back on the gate, then it'll tell me that the FET itself is, because it'll work with one, right? One will work, it just won't work to the right power. Okay, let's just take a look and see whether I get a drive signal. I do not have a drive signal. I don't have a drive signal, so it could be the IC that's bad. I think the FET is okay. I've got two of them here. Okay, we measure it. We got open, and if I touch the gate, it'll go into conduction. And then I release it, and it goes back out. And there's nothing between the gate, between the source and drain. There's nothing until you bring the gate into conduction, and then you've got your switches on, and now it's back off. Another one here, exactly the same, right? This is one's the original, one's the other one. So it's going to be the IC that's shot on this thing, unfortunately. So what I'm going to do is I'm going to swap the transistor with the one from the top here, which is just the filament control, because I know the transistor works. It's the drive IC. It's going to be the fault, but I'm going to swap them anyway because they're identical transistors, and we'll see that this one will turn on the filaments. They'll heat up and everything. Let's get this thing in place here. So I could power it up now and the filaments won't come on. We'll put this one back in place. What this is there for is just to provide a delay turn on, so that when you apply power, it waits a couple seconds before turning on the power to the filaments. That's all. They solder down the drain on these so that it acts as a heat sink. Okay, let's turn this thing on and watch the smoke come out. It's going to do the same thing, guaranteed, because we have no drive. I put my scope on here. Yeah. I saw a bit of waveform there, but I think it looked the same as the other one. What that waveform we saw feeding back, because I had nothing when I didn't have the transistor and I had a flat line. What I'm seeing is the pulse kicking back from the transformer. I'm seeing it going back through the FET and appearing on the gate. That's just a lower signal. There is no drive coming out of this IC to drive it, and that is what's happening. Is because of that, the voltage is low, and of course I swapped the two FETs around, so the one that was in here is now up here controlling the filament, and as you see, the filaments are coming on, so the FETs are fine. It's the drive IC that needs to be replaced on it. So now the thing is, I'll have to contact the guy that owns this thing, and we're going to have to order, because this is a PIC, it's programmed, and it's going to have to come from the manufacturer. There's where we stand. We'll do another video on this thing once we get the part in to fix it. So here's pin 16. Actually, we'll look at pin 15 and 16. So here's pin 15 when it turns on. Okay, there's pin 15. Pulse is starting to change, going into a square wave, and then here's pin number 16. You see, it's the wrong. That's just feeding back from the other one. That's what it's supposed to look like. On mine, they look identical. And then it'll shut off. Just like that. So what's happening is the PIC has a timer in it. It gives the system a certain number of seconds for all the voltages to stabilize, and because the power supply is not putting out enough power, the pins 1 and 2 are going to the wrong voltage. I think what's happening is that the tubes are showing a little bit excessive current, only because the B plus is low, and what's happening is because only one of the FETs is working. The other FET is trying to compensate, and it's going into a higher current mode than it should, because only one FET's running, and it's actually triggering an overcurrent shutdown on the PIC because only one FET's working. Anyway, we'll get the part, we'll replace the IC and then go from there.